So now we are going to do the last of the section 6 topics. So here we are, impulse momentum. So that's section 6.8 or lecture number 25. And this is very much straightforward on the linear momentum. The sum of the forces is going to equal the change in the linear momentum of the system. And in angular momentum, it's also similar. You can take the sum of the moments about g, the center of mass, is going to equal the change in momentum about g, angular momentum about g, and the sum of the moments about a fixed point is going to equal the change of moments about a fixed point. Now, if you've been wondering, oh yeah, what is angular momentum? Here we have it on the formula sheet. So the momentum is going to be r. For a particle, we'd have some radius r crossed with mv. And now for a rigid body, when we integrate this about some fixed point, it's I bar omega plus mv d. And about a fixed point, you would just have or about the center of mass, right? This term would be 0. So that's easy to remember. Now let's look at sort of an example problem that makes this a little tiny bit difficult. Like you might not have expected. Let's start with this. So this is a dynamics instructor. She wants to show the principles of angular momentum. So here she's got, she's on this little rotating platform, and she's got this spinning wheel, and it starts out rotating at some big omega here. And then she's going to turn this wheel so that it goes the other way. And we have some of the parameters here in the problem for 6,199. But what I want you to think about is now what is the angular momentum for a problem like this? Now we want to conserve, we know for this problem, we want to conserve angular momentum about a fixed axis. We can't, it's not necessarily going to be the center of mass here, because like this may be heavier, or maybe would offset her center of mass, so her center of mass would kind of be somewhere in between here and there. But it is a fixed axis, right? So this axis here that would go through the center here, this is a fixed axis. And about this axis, there is no moment applied, right? So she's free to rotate about this axis and it's fixed. So we want to do conservation of momentum about a fixed axis. So let's think about what's happening before. If we look kind of at a top view, so this is her head and this is the wheel. And so the wheel will have some angular momentum, and like the moment, so there'll be some, this little piece of mass here will have some momentum in this direction. This little piece of mass will have some momentum in this direction. These little pieces of mass will have these kind of different velocities. And then after she rotates it, if you're still looking from the top, the whole person and the object she's holding they're all going to be rotating together. So if this little piece of mass on kind of her hair has a velocity of this much, then the tip of the wheel is going to have a velocity that you can predict with this line through it, right? Because it's going to be rotating. All right, so let's derive this formula real quick, so that we kind of make sure we're understanding all of that. So to understand this, if you have some fixed point O and some center of mass G, now you're going to also have some vector between the fixed point and the center of mass, and let's call that D, and some vector here that goes to every piece of our mass. We'll call this dm. And so angular momentum can also be written h equals the integral of all of the moments of momentum. So r, so it's about a fixed axis, so h about o, r cross all of our little tiny pieces of momentum, right? Differential pieces. So, and we can rewrite that here like this, r cross v for each piece of mass. And so we'd be integrating this for the whole mass. But now, here's where we can kind of simplify things. We can say that really this vector r is actually going to be this vector here. So that's actually going to be this vector d between these 2 points and a bunch of these vector rows. So we're going to say d the vector plus rho the vector crossed with, and now the same thing, this velocity, and we want to care about this velocity of this point. But actually, what we can do is we can think about that as the velocity of the center of mass, which is a vector, plus omega cross our vector rho. And now all we have to do is integrate that, which may not look easier at first, but if we break down these components now, we're going to have some d cross v bar. And actually, these are both constant for all the masses, so we can bring that outside the integral. And then we're going to have some d cross omega. But actually, both the d and the omega we can bring those out of the integral because they're going to be constant for all of the different pieces of mass. So we'll just have cross with, so that's this part. Oh, but now, fortunately, we've defined our rho vector such that the integral of this over all the different masses, that's going to be equal to 0 because of how this is defined. It goes from the center of mass, and so because it has to be symmetric, then this is going to go to 0. And now we're going to have I already did all the ones that are crossed with d. So now we're going to have our rho vector crossed with our v bar vector, but we can actually take this v bar out of the integral. So we can have that rho vector, dm, take that integral, crossed with v bar. Oh, but again, this term, because of symmetry, when you integrate all of the vectors between the center of mass and all the points, the weighted average of that over the mass, that's going to go to 0. So again, this is another term we can ignore. Plus, now we have this cross this term. That's our last one. This rho cross omega cross rho. All right, and so now this should start to look sort of promising because we can have this vector and this vector are always going to be perpendicular if this is out of the plane, right? These are perpendicular, so now this is not going to go to 0, but it is going to be the same as pulling this out here, right? So now this should look pretty familiar. This is a moment of inertia equation, so now we can say that HO is going to equal, this is just going to be the total mass times d. Now this is not even a vector, this is just like the magnitude of that distance between the center of mass and the fixed axis. And now we just need the velocity of the center of mass that's perpendicular to this, right, plus I bar omega. So that means that the angular momentum vector about any fixed point is going to be equal to I bar or omega plus this other term. Yeah, so there may be problems where you need to use this kind of formulation. In this case, it kind of works out pretty simple because this point isn't moving, so it's going to have an initial velocity of 0. So let's go back to our example problem. Okay, so we have our wheel before, and so I was gonna like try to prove that out here, but there wasn't enough room, so I just erased it. And now we have the angular momentum initially is going to be I bar plus this mvd, but of course this term is going to be 0, so we don't need that. And we have the I bar because we have the radius of curvature up here, radius of gyration, equals 0.3 squared, and then we've got 10, and now we have how fast it's rotating, which is 250 times 2 pi over 60. And now here on the other side, this is where, I'm trying to make this a little darker so you can see it. This is where we're going to have the teacher, which is what we're supposed to be finding, this I about the teacher, times omega. And then also there'll be some contribution of the wheel. And so it's going to have some MVD term, but it's also going to have, you're going to have to estimate now the moment of inertia of this wheel when it's rotated this way. And now if you go back to your formula sheet here, this is like maybe one kind of trick to this problem, is that a cylinder, when it's on its axis, like normally when you rotate some disk or something, you're going to have 1/2 mr squared, but then when you rotate it the other way, it's going to be 1/4. So we're just going to guess that whatever we were doing before with this k squared m down here, that when we rotate it, it's going to be half that. And the omega that it's rotating in this new sense is now the new omega. And I guess, so I should have probably used this omega here is capital omega, right? And this is some new omega, which they tell us is 30. Okay, so all of these are rotating with that. It doesn't matter that it's rotating in this direction, because we're only talking about the conservation of angular momentum out an axis that comes out of the paper like this. So that momentum doesn't matter. All right, so here we have this, and we just plug things in. So we're going to have I, which is the teacher that we're looking for, and we have this MD term because, of course, the velocity of the wheel at the center of mass is just going to be this omega times that d. So we can pull that out here. And then, like I said, there's that trick where we're just going to take 1/2 of whatever our wheel was before, use that as an estimate, and then we start plugging things in. And I wasn't sure how significant, these types of terms would be compared to the total, so I wanted to have some numbers here, because, maybe if the wheel's light enough, then it hardly even matters, right, if you have a heavy enough teacher. But it does look like this is sort of starting to get such that it would matter. So then when you solve this out, you will get, in fact, that I of the teacher is going to be this 3.45 number.